Recording's about to start. Yes,
And
we
share
are
the
live.
screen. Okay. So, hello everybody. So today Sidharth will be giving a talk on relativity in the most minimalistic sense possible. It's a paper by Palash uh, B Pal. I think that's the name. Yeah, Palash B Pal. And uh, this talk will take about an hour. And this paper actually talks about relativity using only the basest assumptions. You will be going through some amount of elementary group theory with some examples and then follow the proof of the paper. So this won't have too many prerequisites, but I think the minimal amount of prerequisites are something along the lines of having done your UG first year.
Yeah, none at all. I just want you to know what a partial derivative is.
Okay, so the only requirements are knowing what a partial derivative is. Okay, so Siddharth, please start.
Yeah, thank you. All right. So, hi guys. So essentially, the goal of this talk is to try to get to the coordinate transformations that keep the laws of physics intact, which is essentially what Einstein and Newton tried to do, which was found later on. But assuming as less things as possible. To explain this statement first, I want to explain some basic group theory. So let's start as follows. Let's take a very basic example. I have an equilateral triangle and I label its vertices A, B, C. The thing I'm trying to study here are the symmetries of the equilateral triangle. Right? So let's say the equilateral triangle is only on the plane. It's not in 3D. So by symmetries, obviously, I mean I do something to the equilateral triangle, but in the end, it has to be congruent to the original equilateral triangle. So I could rotate it by 120 degrees in some direction. A, B, C. This is a symmetric triangle, right? Let's say I call this original triangle E. Right? What I'm interested in is what did I have to do to get from this triangle to the other triangle? I had to do a rotation about the circumcenter or the center of the triangle by 120 degrees. So let's call that function, which actually does the transformation on the plane, as let's say rotation, right? So I apply rotation to this triangle E, it gives me this other triangle. So let's say I apply this rotation to this triangle again. I get another symmetric triangle. I am specifically labeling the vertices to show you that the equilateral triangle that I've got is a different one, but it's symmetric. It's a rotated one. So I apply the rotation again and I get this one, right? What happens when I apply the rotation a third time? I don't have to draw it again because I come back to the original one, right? So this is again by application of rho. But then you look at this and you're like, hey, forget rotations. There's another type of transformation that I can do that still preserves the congruency or the symmetry of this triangle. I can reflect it, right? So reflection kind of changes the orientation. Right now, the ABC are in counterclockwise labeling. I can get from here to absolutely the same triangle, A, B, C. Oh, let me reiterate that by symmetry, I mean that I'm not changing the position of this equilateral triangle. I'm saying that when I do the first rotation, A goes to the position of C, that particular coordinate on the plane. Like if I were to label the XY plane, and C goes to the coordinate of B and B goes to the coordinate of A. So it's not like I'm rotating and then putting it somewhere else. So that this is just figuratively speaking, the maps that I've drawn. So I could reflect it. So B goes to the position of C, C goes to the position of B. And let's call this map re, right? And I could do the rotations for this also. And rotation was A, B, C. And you see how they're distinct from the rotations above, right? So I can do one of two possible things. I can rotate, I can reflect. And the thing you notice is if I reflect twice about, so reflection is going to be about this axis. This particular reflection is about this axis. But you actually see that it doesn't matter. I have drawn 6 equilateral triangles here, and you can get from any one to any other by either rotating and then reflecting, or some combination of rotation and reflection, right? So this study that I have done, the study of symmetries of the equilateral triangle, is basically what group theory is all about. It's about studying symmetries. It's about studying symmetries of something. In this case, I have 6 possible types of triangles, but what I'm interested in is the functions that, or the actions that I have to do to those triangles to obtain the other triangle. So one obvious symmetry of a triangle is the function that just takes it to itself. It's the identity function. It's just f of x equals x for all x in the plane, right? So what I'm interested in are these functions. So if I have to write these functions down, I'm starting with the initial equilateral triangle that I'm named E. So the symmetries are the identity function, which takes it to itself. Rotation applied once on the initial map. Rotation applied twice, I'm going to write as rho square. And rotation applied thrice brought me back to the original triangle, which is the same as the identity function. So I won't write rotation applied thrice as a special function. It could be reflection. It could be rotation composed with reflection, and rotation square composed with reflection. That's precisely what I have written. So this triangle here is rotation square times reflection. And I'm not going to write reflection square because that's the identity map again, clearly. So I hope there's no problem till here, because now you see the number of functions that are here, right? There are just 6 functions here, and there are 6 triangles. Each triangle corresponds to a function, because here is some jargon that I'm introducing. The function acts on the initial triangle to get the desired triangle. So this set here, I'll call this set D3. D3 because it's actually a special group with its own name. So D3 is the set of symmetries of an equilateral triangle. Now, by set is just something with 6 elements, but this is a special set, right? Because I can take any element here, and I can, in a sense, compose with another element. So let's say I apply the first rotation, I go to the first triangle, right? And then I apply a reflection. So I have rotation and then a reflection applied to it. So what triangle would I get to? So let's say I start with triangle ABC. So I apply rotation first. Rotation was anti-clockwise. So I basically get this figure here. So I get A, B, C, and then I do reflection about this axis. Now that gives me B, A, C. But you see, that's this triangle which I've already listed here. So you see something very interesting. Regardless of this, you can work out explicitly for all types of combinations. But you see that I take one function here and I compose it with another function here. I still end up with a triangle. Like when I act it on the original triangle, I still end up with a triangle that was already listed as some function here, which was rho square applied to reflection, right? So this is very interesting. It's like I take any 2 functions and I compose them. What I end up with is a function that's already listed in the set. And this is the additional property that a group has, that it's not just a set, because a set is just informally a collection of elements, but it's a set with this special property that I can compose, or what's technically called multiply 2 elements, such that if I multiply 2 elements, the product that I get is still going to be listed. Now, a group also has another special property, that it has this identity element, which basically does nothing. And finally, you see that corresponding to every element here, like rotation has this complement function, rotation square, that when I multiply or compose rotation times rotation square, what I end up with is the identity. So you see, it's some sort of a inverse function, inverse product, like it's an inverse to, it's a multiplicative inverse, so to speak. And again, corresponding to row square, if I multiply it with row, I get the identity. With reflection, if I multiply it with itself, then I get the identity, right? Yeah. So this I'm taking this particular group as an example to distill the properties that a group has. All right. So I hope everybody's clear with this example. Like what a group is isn't these triangles, although it could be associated with all of these different triangles. Like this particular group, I mean, D3. What D3 is this set of 6 functions with a special property that they can be multiplied with each other or composed with each other. And there's an identity function in this group. And corresponding to every function, there is an inverse function that when you compose them with each other, I get back to the identity. Now, clearly, you notice that this composition, as in this product that I've written here, isn't a commutative product, right? Because reflection applied to rotation gives a different triangle than rotation applied to reflection. Reflection applied to rotation gave this triangle, while rotation applied to reflection gave this triangle. In some sense, this multiplication or this composition isn't commutative. So that's a property that all groups can't have, like in general. With this example that I have to define a group, I will list out the properties of a group. So group is a set G such that if I take any G and H, which are elements of this G, then GH is also an element of G. All right. So this is the first property. Also, I need, before I even come to this properties, I need to say that this group G has a property multiplication. So I just write that as dot because I'm not really referring to it here. So it's G dot H. So when I write a group, I usually write this pair G combined with this product map that's there, right? So it takes two elements from G. This is basically like G cross G is the Cartesian product. It's an ordered map, ordered pair. Sorry. So it takes two elements of G and it outputs an element of G. That's the product. So yeah, so you take G and H that belong to G, then the product belongs to G. And there is a unique element E which belongs to G such that G dot E equals E dot G equals G. So this E is called the identity element of this function, of this multiplication. Or you could even say the identity element of this group. Now, the third and final property is that corresponding to every G, small g is an element of big G, there exists a unique element, G inverse, such that G dot G inverse equals G inverse dot G equals E. Right, so these are the three basic properties of the group, of any group. And you can see all of this in the previous example very clearly. So corresponding to any two functions here, like you can multiply any two functions, and corresponding to every function, there is an inverse. But before that, what does the function times an inverse do? It gives the identity. So there must be an identity. You might ask me, why should there just be one identity? There can be more than one multiplicative identity. All right, so let's say there were two multiplicative identities that satisfy property 2, like without the uniqueness, obviously. So E times F, what would that be? Well, E is an identity, so E times F just gives F. But then F is also an identity, so E times F shouldn't change the value of E, right? That's where the uniqueness comes in. This is just an illustration to show that the uniqueness is a property that you can just get. But in essence, these three additional properties, when given to any set, along with some multiplication on it, make up a group. And you might ask me, what are examples of groups and how are they in general related to symmetry, right? Because the example that I just gave you before, D3, was just the symmetries of a equilateral triangle. But if I just give you these three axioms or properties, how do they relate to symmetry? So this question in general is kind of not so easy to answer, but I hope I can convince you with enough examples. All right. Of course, I don't want to bore you with examples of symmetries of a square or a pentagon or so on, or a regular pentagon and so on. I'm going to give you this example: the integers with the property of addition. So when I say multiplication here, that's just the name I give this dot. Okay, this dot is just a map that satisfies these properties. So the integers with the addition property. So clearly, if I add 10 into integers, I get an integer. And clearly, there is the number 0 that I add it to any number both ways. I get the number itself. And corresponding to every number n, there's the number minus n. So that when they get added, they give 0. The integers is a special group because this addition is a commutative property. M plus n equals n plus n. Now, how is this related to symmetry in general? If I were, say, in an infinite building with floors, the floors are labeled with integers. Let's say this is the floor number 0, 1, 2, 3, and so on, minus 1, minus 2, minus 3. Again, this hypothetical example isn't really practical or physical, but it's to give you an idea of, oh, when I see another situation, I can maybe relate it to this. If I'm on any floor of the building, to get to any other floor, I have to add, if I'm on floor number n and I have to go to floor number m plus n, I have to go up m floors. So going up m floors corresponds to the number m. But then since it's an infinite building, regardless of which floor I'm on, the building is going to look the same, right? It's symmetric from where I stand, the building is symmetric to the original building. This is an example, it's an infinite example, but most examples from now are going to be infinite. Let's say another example is the real numbers with addition again. It's easy to say if I have two numbers x and y, x plus y is also a real number. Corresponding to x, there's a minus x, which gives 0. But firstly, there is a 0, which is an identity element. And this real numbers can be thought of as the symmetries of an infinite line on a plane, right? Like if I translate in any direction by any real number, the line is going to be symmetric to itself. But I have to translate in the direction of the line, obviously. Another example are matrices with non-zero determinant, right? Because non-zero determinant, because I want to force that square matrices with non-zero determinant, I want to force the property that every matrix has an inverse. So I'm restricting myself to just matrices that are invertible. Of course, here the multiplication property, the dot property is different because the dot property here is in fact the matrix multiplication. And this group is actually called GL. So don't worry about this jargon because R is just to say the inputs are real. N is to say it's an n by n matrix, and GL means it's general linear. Don't bother with the specifics. It just means it's the set of all invertible matrices. So of course, if I take any two matrices M and N, which are invertible, then clearly Mn is invertible because invertibility just means non-zero determinant. Determinant of Mn is det M, det N. And this is non-zero because each of them are non-zero. So Mn is also invertible. And obviously, if I multiply with the identity matrix, the matrix stays the same. So identity matrix is essentially an identity for this multiplication. And corresponding to every M, there is an M inverse because it's invertible. And M times M inverse equals M inverse times N. Now, the special thing about this that doesn't correspond to the previous examples that I've given is that matrix multiplication isn't commutative. So this is a pretty general type of group, right? What does this represent the symmetry of? Can anybody guess what this represents the symmetry of? I mean, you can either type it in the chat or exactly the n-dimensional Euclidean space. So maybe in your second semester you've seen. So any n-dimensional vector is written compactly as an n-dimensional, like an n-column vector, right? N entries in a column. And if I have a linear function from an n-dimensional vector space Rn to itself, then the matrix is an n by n matrix. And if you want it to be it's a linear map. And if you want it to be an invertible linear map, then the matrix itself should be invertible. So essentially, what I'm doing here is I am drawing on symmetries of Rn to itself, but not exactly so, because you see matrices can scale, right? Like if I take the vector I hat, and if I apply some matrix to it, what I end up getting could be some k times I hat, and that's not really symmetric because it's like a scaled version. So it's a bit more nuanced than that, the symmetries that GLNR represents. But yeah, let's move on. Like as I go to a more specific example, you'll see exactly where the symmetries of the n-dimensional Euclidean space plays a role. So there's another set of matrices called SLNR. So G stands for general, S stands for special. So it's the same properties as before, invertible matrices with the matrix multiplication, except that I have the additional condition that the determinant of all these matrices is 1. Now you clearly see, like from the above equation, that det m times det n is going to be 1 anyway. So this is again a group. Now, like even more specific is this type of matrix called SONR, which is called the special orthogonal group. Special again means determinant is 1. Orthogonal here means I'm sure you've seen how to change bases in your multivariable calculus. Suppose I had an orthogonal basis and I go to another orthogonal basis. That particular linear transformation is called an orthogonal transformation. The determinant equals 1. So the determinant of a linear transformation is in some sense a characterization of how much a vector gets scaled after it gets transformed, right? When determinant equals 1, it means the vector doesn't get scaled at all. And when angles are preserved, so what the orthogonal matrices mean are like the orthogonal basis vectors go to orthogonal basis vectors. And you can show that this also means that angles between any two vectors get preserved. And since their vector lengths are also preserved, what I essentially have is a symmetry of n-dimensional Euclidean space, Rn specifically. So SONR is a wonderful group. In quantum mechanics, a lot of you will see later the specialty of this group called SO3R, which is just the three-dimensional orthogonal group, right? And I don't know, it's like, let's just say SO2R is something you can even visualize. It's just, if I have the two-dimensional plane, I told you that the angle between the basis vectors needs to be preserved. So let's say this vector I hat, this is j hat. So let's say I hat goes somewhere here to I hat dash. So then j hat correspondingly goes somewhere here, j hat dash. Now you might ask me, why not here? That's also perpendicular, right? So it turns out if you want it to go the other way, what you're essentially doing is changing the orientation, right? To go from I hat to j hat, you have to do a counterclockwise 90-degree rotation. And if you were to change that to clockwise, what you end up is determinant of that transformation is -1. So the minus changes the orientation. So there, this SO3 SON is the example I wanted to get at, and I hope SO2R gives you a good feel of this rotation. Like this perpendicularness is preserved, and in doing so, the angles between all sorts of vectors are preserved. Just keep this example in the back of your mind as we move on to the rest of the talk. So this essentially is my basic introduction to group theory for you guys. It's not very rigorous, but I hope I gave you a sufficient intuition for the properties of a group. And maybe when you read up later, it might be easier for you to grasp. All right, so moving on. Einstein, when he came up with his first special theory of relativity, had a number of assumptions which were very implicit. These assumptions were answered almost immediately after his paper came out by a bunch of mathematicians. But those papers that try to minimize the amount of assumptions in physics are very little or are overlooked because that's not really important after the theory is found out. Like it's important in theoretical physics because at some point of time, but it's not really important to appreciate the theory itself, because the special theory of relativity itself isn't an appreciation of the axioms, it's an appreciation of what comes out of them. But right now we're going to look at the basic axioms of physics in general and what could come out of these. Firstly, an axiom of physics is that space-time, for the rest of this talk, I'm going to be concerned with space-time as coordinates x, y, z, t in the space R4, right? So space-time is homogeneous. That's the first assumption that every physicist makes in general. Homogeneous basically means that no coordinate origin is special. Like if I were to perform my physics with my origin somewhere else, I would end up with numbers that reflect the same properties of my experiment, right? And if I have two coordinate systems that were separated from each other, but stationary with respect to each other, it doesn't matter where their origin is if I have properties that just depend on the separation between them, right? So it doesn't matter if I perform my experiment, like if say there was no mass in the universe at all, it doesn't matter whether I perform my experiment here or there. And if I change my origin here or there, that's what I mean, not perform the experiment here or there. So that's what homogeneity means. And there's also the property of spacetime called isotropy. So isotropy in general means that moving in any direction in spacetime should not be special. So moving in one direction and moving in another direction can just be corrected, but there's nothing special about one direction of the universe. All right. So with these two assumptions, I will move on to the main question that I want to address here. So the main question I want to address here is, suppose I had a system of coordinates called x, y, z, t, and let's just label the system S. And now I'm going to deal with only inertially moving frames because that's what special relativity deals with. Let's say I have another system of coordinates, x dash, y dash, z dash, t dash. So the origin of S dash, which was O dash, and the origin of S is O. So O dash moves with respect to O at a velocity v in the x direction of S. All right. So I hope the situation is clear. So I just have one coordinate system. Let's just call this one x, and the other one x dash. This origin is moving at velocity v with respect to this origin in the x direction of this system. All right. I'm also going to make the additional assumption. This is just for ease of computation, that x equals y equals z equals t equals 0 implies. So at time t equals 0 for the system coordinate system S, both the origins coincide. From here, what a lot of physicists assume, of course, not quantum mechanically anymore, but classically, is that this whole coordinates that I have assigned to space and time are in some sense differentiable. Like you have arbitrary closeness between points, but this is not necessarily the case. Of course, this is a fair assumption to make, considering that all physics that you see classically is differentiable. Like velocity is differentiable, position is a differentiable quantity or a parameter that you can assign to as a function of something else. But again, this is not necessarily this is true if you were to speak rigorously. I mean, a fair thing to say would also be that the coordinate systems are continuous, and you'll see what I mean by this when I come to it. The main question that I want to address here is, what are the types of coordinate transformations from what is the coordinate transformation that will lead me from x to x dash? All right. So let's say that x dash is some capital X of x, y, z, t, and of course it's also a function of v, right? And same for y, it's a capital Y of the same thing, and z and t as well. So notice I'm not taking t dash equal to t because I want to derive the general set of transformations. So I can write this in compact notation as some w vector equals some function, w vector dash equals some function of w vector, where w is the vector x, y, z, t, all right? And fv has the components capital X, capital Y, like capital X which acts on X, capital Y which acts on Y, capital Z which acts on Z, and capital T. So this is the notation that I have. And with this, what I want to prove is that the coordinate transformation that will lead me to the x dash system of coordinates is actually a linear transformation. That's very special, right? Because there's so many types of coordinate transformations that you could have, but it happens to be linear given the assumptions that we have. So let's take some points, some fixed points, x naught, y naught, z naught, t naught. All right. And let's also take some arbitrary real numbers, delta x, delta y, delta z, delta t. All right. Also corresponding to this, let's say I have delta x dash, delta y dash, delta z dash. And I define these quantities. Now, these are not changes right now. These are not changes of any quantity per se, but I will attach them to changes of certain quantities later on. I will just define this function delta x dash equal to capital X of y naught plus delta y and so on, or z naught plus delta z, t naught plus delta t, minus x of x naught, y naught, z naught, t naught. Now you clearly see that delta x dash is a change of something. Like it's a change of x at the point this, and versus the x at the point at this shifted point. So here right now delta x, delta y, delta z, delta t are changes in quantities right now. Now they're arbitrary changes because I'm not saying delta means a small quantity. This could be absolutely anything. So I have this equation defined for delta x dash and correspondingly for delta y dash and so on. Now here's the thing. Here's something special. Let's look at the system delta x, delta y, delta z, delta t as some coordinate system s hat. All right. Now this is absolutely identical to the coordinate system s, right? But its origin is at the shifted point x naught, y naught, z naught, t naught, right? Because at x naught, y naught, z naught, t naught in the system S, what we will get in the system S hat is the origin, right? And also, if we had x naught dash, y naught dash, z naught dash, t naught dash, which I haven't written before, but x naught dash is basically this quantity, x of x naught, y naught, z naught, t naught, and so on, y naught dash and so on. In this is in the S dash system, right? Now corresponding to that, I will take this delta x dash, delta y dash, delta z dash, delta t dash, and call this system of coordinates as hat dash. Now S hat dash is identical to S hat, S dash, except it's shifted, right? It's just shifted. It's just a shifted origin. It's not moving. It's stationary with respect to S dash, but it's shifted. Now, I'll just use rough terminology to say they're equivalent. To go from S to S dash required a certain set of transformations that I described earlier as F subscript V, right? what homogeneity tells us is that no coordinate system is special with respect to origin, right? So S hat is not special with respect to S. It's just a shifted origin, and S dash hat is also just a shifted origin of S dash. Here's the wonderful property. Delta X equal to delta Y equal to delta Z equal to delta T equal to 0. Like if I take the origin of S hat, from this equation, you can see that you just get X of X naught, Y naught, Z naught, T naught minus itself. So delta X dash is also 0. And this is the same for all the other quantities as well. And this is the exact same assumption that I had for my original thing right here. Like my relation between S and S dash was this. So now there's absolutely no difference between S hat and S dash hat and S dash. It's like the relation to each other is also that they have a common origin. Like when time delta T equal to 0, then the origin of S hat corresponds to the origin, the shifted origin of the other one. So the relation between each other is the same as the relation between S and S dash. And homogeneity, the magic of homogeneity is that it tells me that delta X dash should in fact be just X of delta X, delta Y, delta Z, delta T. Like there's nothing special. There's no different function that defines two coordinate systems that have the same relation, which are stationary with respect to their old coordinate systems. That was a very long sentence, but I hope you get the point. Now, I'm not going to write the equation for Y, Z, and T. Now you see this equation that I have here. I'll just replace this delta X dash by this function that I have here. So X of delta X, delta Y, delta Z, delta T equals X of X naught plus delta X and so on, minus X of X naught, Y naught, Z naught, T naught. So I'll just take this to the other side. What it tells me in the end is X of X naught plus delta X, Y naught plus delta Y, and so on equals X of X naught, Y naught, Z naught, T naught plus X of the change. That's very neat, right? But this still doesn't show linearity. Like this is just a cool quantity. So this is the same for the capital Y, capital Z, and capital T, but combining them all together in the form of the function fv means that fv of two vectors, because this is some vector, this is some vector. Fv of two vectors w plus u. V is the velocity here. Don't get it confused with any other vector that's there. It's just some fixed velocity in the x direction that we have. And keep in mind, this is the same velocity for the S hat system also, because again, it's just translated the origin, stationary with respect to the original system. What this is telling me is this is the sum of the functions on the individual positions. And the special condition is that fv of 0 is 0. That's what this condition right here means. So now I have some very cool thing on fv. What I can tell you now is what's f of k times some vector v for k belonging to integers. You can verify that this is actually k times f of w, because of course f of 2w is f of w plus w, and that's f of w plus f of w, so that's 2f of w. And you can proceed by induction for any integer, all right? And also you have that f of w plus minus w equals f of w plus f of minus w. But this is f of 0 on the left side, so this is equal to 0. So f of minus w is minus f of w. So we have these cool conditions right now that integer times a vector. If you apply the function, it's just the integer just comes out in the multiplication. Now we are getting closer to linearity, but we have only done this for integers. So let's say I have f of w by n, all right? Some n is some integer again. Now I multiply this by n. This is going to be n times f of w by n. But what's on the left side? That's just f of w. Bad handwriting, messed that up. So f of w by n is actually 1 by n f of w. So this is cooler because now this allows me to extend to the rational numbers, because for any q equal to m by n, also here you have to keep in mind n is non-zero. For any q equal to m by n, f of q times w is actually f of m by n times w. So the m comes out first, the n comes out again, f of w. So this is just q times f of w, right? And this is true for any rational number now, that if I multiply q times w and take the function, the q just comes out. I've ignored the subscript v here, but just keep that in mind, okay? Yeah, this is where the notion of continuity comes in, because I didn't know for certain whether my coordinate transformation is continuous or not. What Einstein assumed is that the coordinate transformation is differentiable, which is a stronger condition and of course a very reasonable one. What I'm going to assume is it's continuous, and continuity just implies that it's differentiable directly, because you can just, first of all, you can extend this continuity to real numbers and say that if I have any real number x, I can take a sequence of rational numbers such that they converge to x, and I'll assume this function is continuous. This is an extra assumption that I have to make, and then I can get that the value of the convergence of the functions that I have here is actually the value of the function at x itself. Again, this must be something you've seen in your analysis course, and it's just a small amount of work. Again, epsilon delta, you can verify that with these properties the function is differentiable as well, right? Why not? Hell, let's just do it. So you want to verify like the function is already continuous. You want to verify it's differentiable. So let's say we are verifying differentiability at some point x. So what we want is this particular limit to exist. That's what we desire, right? Limit as epsilon goes to 0. I can take out the x and epsilon separately. So that becomes f of x plus f of epsilon, but the f of x cancels out. So it's just f of epsilon by epsilon, this limit. But again, I can take the epsilon out as epsilon times f of 1 by epsilon. So that cancels out. Limit as epsilon goes to 0. And this limit exists for sure. This is just f of 1. So this function is in fact differentiable. And this is so cool. Like we have that the coordinate transformation is from this, we have one more important thing, that this derivative is a constant. And constant derivatives just automatically tell us that it's linear. And I've only taken the x coordinate changing here, but this basically means that the partial in x is a constant, so it's a linear function of x, and similarly it's also a linear function of y, z, and t. So I can write fv as actually some matrix A, which is some 4x4 matrix, right? Now this is the spicy part of the talk. So I'll open a new page for it. Now for the rest of this talk, I'll just be dealing with x and t. Just trust me that you can extend it to 4 dimensions, x, y, z, t. So for x and t, my coordinate transformations are, let's say I'll just write x as, capital X as some function AV times x plus BV times t. Now these are constants if I keep the velocity constant, but I don't know if I vary the velocity, what could happen to them, right? And capital T as some function CV times x plus dV times t, all right? So in 2 dimensions, I need to write down explicitly 2 properties. One is isotropy of space. So isotropy of space says it doesn't matter what direction my axes are labeled in, physics still stays okay. So suppose my axis was labeled, my x-axis was labeled in the opposite direction, all right? So what that means is I want to take x of minus x. I'm still looking at the same point, but with my coordinate of x reversed. So the coordinate in that new reversed system is a minus x. Time is still the same. My value of velocity will also get changed, right? Because I want my velocity vector to remain in the same direction. So in the new system, it would actually be the negative number, right? So isotropy says that if I change the direction of x in one system, then if I just apply the coordinate change, all it does is change the direction of x. So this will be minus x. Now I'm not touched time. So time of minus x t minus v still stays time of x dv. All right. So this is one set of conditions. And another set of conditions is that what if I want to go back from the S dash system to the S system? All that means is in the S dash system, the S system is moving at a velocity minus v, right? That's the only specialty. So if I were to write x and t as a function of the new coordinate system, it will be x of x dash t dash, but minus v. T of x dash t dash minus v. But again, x dash and t dash I can write in terms of the original x and t. Now this might look a bit scary. I'm not going to write it for t, but again, we have linear functions, so they're very easy to write down explicitly. So my first condition here, I'm going to label this 1, I'm going to label this 2. So my first condition here, if I write it down explicitly in terms of the coordinates, what that tells me is AV is A minus V. Like I'm just expanding this x in terms of AV BV. This x in terms of, like if I were to expand this thing out, it'll actually be A minus V of x and B minus V of t. A minus V of minus x, sorry. So what I get are 4 conditions. Just trust me on this. Like you can work out the details. So A V is A minus V. B of minus V is actually minus BV. C minus V is minus CV, and D minus V equals DV. And from the this comes from 1, and from 2, what I get is a linear equation of a linear equation, right? So actually, let's work that out explicitly. Yeah, so this was the one. So I'll just write it out. X of x equal to capital X of x t v, capital T of x p v, and minus v. So this will be wow, a minus v of this term, right? Capital X of x t v plus b minus v of capital T of x t v. A minus v is AV from above. So it's AV times A Vx plus BVT plus B minus V is actually minus. So BV of CVx plus DVT. Right, this equals x. So the coordinate of t here should go to 0, and the coefficient of t here should go to 0. The coefficient of x here should go to 1 to just match the equation. So, and I do the same thing for the t equation, and what I end up with are these 4 interesting set of equations. AV square minus BV CV equals 1. BV times AV minus DV equals 0. CV times AV minus DV equals 0, and DV square minus BV CV equals 1. So here this is pretty restrictive. So I have two conditions here. Either AV equals to DV or AV does not equal to DV. So if AV doesn't equal to DV, right, what you get is that BV and CV necessarily should be 0. Also, like if you want to visualize it better, like this is AV, BV, CV, and DV are actually coefficients in a matrix that act on the xt to give me x dash and t dash, right? So yeah, if BV and CV are 0, these two terms, if AV not equal to DV, then BV and CV necessarily are 0. That means that AV square is 1, DV square is 1. So that is AV is plus or minus 1, DV is plus or minus 1, but they can't be equal. So that means that either the two matrices corresponding to that are 1, 0, 0, minus 1 or minus 1, 0, 0, 1. Now, both of these are mathematically valid, right? But they aren't physically valid because of one condition. Because both of these state that what happens when I apply them to, say, the vector 0, t. That basically means I'm trying to calculate where the origin would get shifted to, right? Where 0, t would get shifted to. So this will give me the vector 0 minus t, and this will give me the vector 0, t, right? So all this is telling me is that regardless of my velocity, the new coordinate system will have the same origin, only the time will get will get a sign on it, and that's a matter of convention. But this isn't physically possible because we know that the origin is moving at a velocity v with respect to my original origin. We know one fact that the origin of the S dash system, when seen as the origin of the S system, is actually at a time t. Where is it? It's at the location vt in the original system. Just to make this clear, x dash equals 0 implies x equals vt, right? So the origin of the new system when represented in the old system is vt, where t is in the old original time system. So of course, AV not equal to DV is eliminated. So AV equal to DV is what we have to look at. And when AV equal to DV, BV and CV need not necessarily be 0, right? So let's just say BV not equal to 0 for now. So the two conditions that we have is DV equal to AV. And when you solve from this equation for, like, let's just say BV not equal to 0, one of them not equal to 0. So you can write the other in terms of that, right? So you can write CV from the first equation here that I boxed in is AV square minus 1 by BV. So these are functions of just velocity now, correct? And I want to apply this additional condition that x dash equal to 0 implies x equal to vt. So that's in my new thing, x dash equal to 0 implies x, capital X of xt equal to 0. But then my x here has to be vt. That's my restriction. So AV times vt plus BV times t equal to 0, and this holds for all time, not just. So I can cancel out the time factor, because for non-zero time also this is true. So BV equal to minus AV, so times V. Sorry. So this is something additional that I have. So right now, my matrix x dash t dash as a function of xt actually looks very simple now. I mean, substantially simpler, because it's all a function of just one variable. and then AB. This applied to xt. All right. So this is extremely cool for two reasons. Firstly, we established linearity. Secondly, we established that the change is just one constant. That constant happens to just be a function of the velocity. All right. Now, let's say I want to try to find AB now. I'm going to go one step further to try to find AB. AB was specifically for the velocity v, but now let's say I have another system S double dash, which moves with respect to S dash as at a velocity u. All right. So x double dash t double dash is actually this function au minus u times au, and this some function of this u, and then au again here, applied to x dash t dash. But then I can write x dash t dash as above, right? So now I can multiply these two matrices, and I get some big term, some big term here. All right. But now this is some big term times xt. Now s double dash is moving inertially with respect to s dash, which is moving inertially with respect to s. So s double dash also moves with some velocity, some arbitrary velocity with respect to s. So this matrix should actually also be some a of something, right? So, but then it should also follow the criteria in general that the first term equals the last term. So let's just explicitly calculate the first term and the last term. Here it was AV and this term, this big term here. So the first term actually is AU AV plus AV square minus 1 times U AU by V AV. All right. And the last term here is actually this times that. So that you actually get as again AU AV plus AU square minus 1 times V AV by U AU. All right. This cancels out. And what I'm left with after rearranging some terms is AV square minus 1 by V square AV square is AU square minus 1 by U square AU square. This is a very cute equation, and it's very powerful for two reasons. One, this side is function of just V, this side is a function of just U, but this is true for all V and U. I didn't put any restrictions. I mean, non-zero V and U. I didn't put any restrictions. So what does that mean? This as a function of V must be a constant. So now I can solve for AV from this. AV square minus 1 is K V square AV square. So AV I obtain is actually 1 minus root 1 minus K V square. And my x dash t dash, I can take out this factor out, 1 minus 1 by root of 1 minus K V square equals 1 minus V minus K V, sorry, 1 x t. And this is so simple looking, but it's so powerful. Okay, we used homogeneity of space-time, isotropy of space, and continuity of the transformation function, and we arrived at something that is shockingly simple, except for one thing. We are yet to apply it to actual physics, right? We just have a bunch of coordinate transformations. What do we do with this now? How is this useful, right? So one simple way where this is useful is, you guys remember that problems that we had in JE, like if the system S double dash was moving with respect to system S dash with a velocity u, then what's its relative velocity with respect to S? Classically, it would just be u plus v or something, right? But from here, what we can directly calculate is, let's call that velocity w. W, don't get confused with the w vector I introduced in the beginning. This corresponded to AW, all right? This whole term was actually AW. All right. So AW equals AUAV plus AV square minus 1 UAU by VAV equals AV. I'll use this notation here, 1 plus K times UV. All right. And now I can write AW explicitly as 1 minus 1 root of 1 by root of 1 minus KW square, and this is this. And when I solve, what I get is W is actually U plus V by this equation should look familiar to those of you who've studied relativity, and why it looks familiar will come just in a moment. So x dash t dash, I'll just write this here because these are the two magic equations that I wanted as the goal of my talk. Sorry, KV. Now, until Einstein, what people assumed was the universality of time, right? That's what Einstein disproved. That's the whole the Michelson-Morley experiment got the ball rolling, and Einstein kind of like time is not absolute. What that means is before Einstein's time, what people assumed was the simple fact t dash equals t. So t dash equals t means that this term here equals 0. And this term here equals 0 for any velocity implies k equals 0. All right. So what would our relative velocity look like? Relative velocity would just be the sum of the two initial velocities. And our coordinate transformations would transform into something very familiar, which is x dash is just x minus vt. That's the relative velocity equation that we've all known until 12th grade, right? What Einstein assumed instead is the constancy of the speed of light. That's the only extra assumption on top of everything for special relativity. Special relativity says, okay, space is homogeneous, space-time is homogeneous, space is isotropic, and the speed of light is constant. Now, the speed of light is constant means one thing. Let's say, like I was in a system S, and system S dash was traveling at the speed of light, but system S double dash was traveling at some finite velocity. So what would system with respect to S, of course, what would S double dash look like with respect to me? So Einstein says that it doesn't matter, it will still be C. So he's basically saying C equals C plus U by 1 plus K C U. All right, so I can solve for this by saying C plus K C U C square U equals C plus U. K equals 1 by C square. And literally, K equals 0 and K equals 1 by C square is the main difference between classical mechanics and special relativistic mechanics. And we didn't even have to go the way of the thought experiments and all that big derivation. Of course, that gives us a much better physical picture. But look at how elegant this is. This establishes that all coordinate transformations are linear, and it's a linear function whose coefficients depend on the velocity and some constant. And the way you treat that constant is the way you treat physics. And yeah, this is where I'd like to stop, and I'd like to take questions if there are any. That's a good question. See, yeah, like if k is 0, clearly regardless of what velocity was there, nothing would happen to the root, right? As long as if k is non-zero, there is obviously a velocity after which kv square greater than 1. In special relativity, that particular k is taken to be 1 by c square, which leads us to say that the maximum speed is c. So depending on what k is, like again, actually you could go one step further and say that all non-zero k could actually be boiled down to 1 by c square after a sufficient change of units. Yeah, so the main point that I completely forgot to make is that homogeneity and isotropy also leads us to say that coordinate transformations are obviously like coordinate transformation as a function of velocity. If I take coordinate transformation as a function of one velocity and a function of another velocity, then like kind of combining them together, which is what I did here with the s double dash, gives me a coordinate transformation that corresponds to a third velocity, aw, right? Also, coordinate transformation in the direction v and the direction minus v are invertible. Like they're kind of opposites of each other, because if I do one coordinate transformation and then I come back minus v, I'm going to get back to my original system s. And obviously, there's the transformation where you don't travel at any velocity, where your coordinate transformation is just the identity transformation. So in essence, the coordinate transformations are a group of coordinate transformations, and they're closely related to SO3 in the sense that this is in 4 dimensions, for example. Like if I were to look at completely arbitrary coordinate transformation, I also have to take into account that obviously there's a change because of the speed, but there could also be a change because of rotations, right? Like normal rotations, the usual rotations that we have. And these usual rotations are precisely SO3. So some combination of SO3 and these boosts together gives us the Lorentz group of transformations. So yeah, this is essentially what I wanted to stress upon as final points. And precisely to stress upon this, I wanted to give you guys a feel of what groups are.